The last section in set theory has to do with infinite sets. And there's some unique things that happen with infinite sets. Now, I will say that the rules that we showed in the last section about those complex set operations, those still work. The subset stuff still works. You can draw Venn diagrams in the same way, whether there are infinitely many things in a set A or finite number of things in a set A. Venn diagrams still all work. So the stuff we've gone over would have still worked for infinite sets. All right, so let's take a step back and recall what equivalent sets mean. Equivalent sets, remember, just had the same cardinality. So for instance, the set A, B, and C, the set ABC and the set containing 1, 2, 3 are equivalent just because they have the same cardinality, right? They both have cardinality of 3 and therefore are equivalent. The set California, Texas, New York, Florida, Illinois, so the top 5 states in terms of population, and the top 5 states in terms of land mass also are equivalent. Now, we've said so far that equivalent means the same cardinality. But there's a more general way to define equivalency, okay? And that's by finding a mapping. So let me just describe what I mean. If I take this first example, I could have mapped A to the number 1. And I could have mapped B to the number 2. And I could have mapped C to the number 3. All right? And that would have been a 1-to-1 mapping. And when I mean 1-to-1, I mean for each of these arrows, it goes out of one element and it goes in to one element. So B goes out to 2. C goes out to 3. All right? Something that would not be 1-to-1 would be something like this. If A went out to 1-to-1 mapping, went out to 1 and 2. Or another thing that would not be a 1-to-1 mapping would be if I had A and B both going to the same number, like a 1. Okay? So, in general, this should remind you, if you saw function notation, all we're saying is that there's a function from one set onto the other, and that function is a 1-to-1 function. So we don't have this idea of, splitting or going into the same number. All right? Now, that takes us to the idea of infinite. All right? The idea of infinite, it's kind of a hard concept to describe. And there was somebody whose last name was Cantor, who lived in Europe a long time, well, not quite a bit ago, that actually really dove in to the idea of infinity, and infinite sets in particular. And in fact, it obsessed Cantor to the point that he went a little bit crazy. And you can read that, read up on that if you want to, but I won't spare a lot of time right now. Okay? And what Cantor did was he said, well, infinite, we think of it as going on and on forever. But a better definition is that it can be put into a 1-to-1 correspondence with a proper subset of itself. So let's look at the example of the natural numbers, the counting 1, 2, 3, 4, 5, and so on and so forth. All right? Now it has a subset of even numbers, right? If I just pull the 2, the 4, the 6, the 8, and so on and so forth, But there is a one-to-one mapping from here to here. Remember I said a one-to-one mapping is just a function. So if I take every natural number, let's call that natural number n, and I just multiply it by 2, all of a sudden 1 maps onto 2, and 2 maps to 4, and 3 maps to 6, and so on and so forth. So this function is a one-to-one mapping that takes the natural numbers onto a proper subset of itself. Okay, a one-to-one correspondence with itself. So then this is one way, this is Cantor's way, in fact, to show that a set is infinite. Now here's where we get into the weirdness of infinity. The natural numbers, therefore, have a one-to-one correspondence with the even numbers. And we just said that equivalence sets, meaning having the same cardinality, have a one-to-one correspondence with each other. So that means the set of 1, 2, 3, 4, and so on and so forth, out forever, is actually the same size as the set 2, 4, 6, 8, out forever. Okay? They're both infinitely big, but moreover, they have essentially the same infinity. They are the same size. So even though the evens are a subset, they do have the same size. Now, what we've just come across is the idea of having a countable infinity. Now, what I mean by countable infinity is this. The natural numbers you can count, 1, 2, 3, 4, 5. Even though they go on forever, they have this nice counting property where we can count them. All right? And so we say, yes, this is infinite, but it is countable infinite. You could sit down and you can count up to whatever number, what number you want to in this list. Okay? So the even numbers are also countable. So they're also countably infinite. And I will say this, that the symbol here, aleph not, if you're ever reading math text, that usually means countable infinity. All right? That's aleph not. It's a Greek letter with sub-zero. All right, for anybody who cares. So countable infinity is an interesting thing. And we can ask things like, is the set of integers countable? All right? So obviously, this is a set that's, in one sense, bigger than the natural numbers, because the natural numbers are just the positive parts of this, okay? And all of a sudden, we've added some negative parts. But it turns out there is a one-to-one mapping that can take the, that can take the countable numbers onto the set of integers. Now let me explain what you're going to do. We are going to take all of the odd numbers. We're going to take 1, 3, 5, and 7, and so on and so forth. And we're going to map those to the positive side. And we're going to take 2, 4, 6, and so on. And we're going to map those to the negative side. And you can see that this is going to be a one-to-one mapping. All right? And so it turns out that the set of integers is, in fact, countable. Now, you can describe a closed form for this. If I say f of n, right, we said we want to take odds to this. So what we're going to do is, so if I have a 3, so if we have an odd number, first off, I'm going to subtract 1, and then I'm going to divide by 2. Whoops. So 3 subtract 1 is 2, divide by 2 is 1. 5 subtract 1 is 4, divide by 2 is 2. 7 subtract 1 is 6, divide by 2 you get 3. 1 subtract 1 is 0, divide by 2 you get 0. So if n is odd, that's what we get. Now that'll take care of all of those. If n is even, what we do is, well, we just take negative of n over 2, right? So negative 2 over 2 maps to negative 1, and so on and so forth. So if n is even, we map it to the negatives. If n is odd, we map it to the positives. Notice that we have this one-to-one correspondence. So anything that I find in the natural numbers, I can figure out anything I can find in the integers, I can find a natural number that maps back to it. All right. All right, so here's what I want you to do. I want you to take a look at the next two sets. Here we have 525, 125, 625. That's obviously different powers of 5. And we have 3, 7, 11, 15. Notice that each time we're jumping by 4 units. And I want you to take a look at these two sets. Ask yourself, are these things countably infinite? And if they are, try to find a function which takes the natural numbers, that is 1, 2, 3, 4, 5, and so on, onto the set. So find a one-to-one function that does that. So again, push pause on the video, try this on your own, and then come back to it. All right, so I hope that you said in both cases that they're countable. In fact, you can kind of see that if you can list the numbers in some sort of a natural progression, it's almost always going to be a countable set. All right, and so this one is countable. And the function that we want is we want powers of 5. So we're going to map the first, in other words, we're going to map 1 to 5. We want to map 2 to 25, 3 to 125. So what you see is we're going to take 5 times itself that many times. So 5 to the nth power. Okay. So yes, it's countable, and it's countable because of this function. And on a test or a quiz, that's what I'm going to ask you to do. I'm going to ask you to determine if something is countable or not. And then if you can, then if it is countable, give me the function. All right. Now the next one's fairly straightforward again as far as countable goes. Yes, this is countable. We can see that because we have some sort of a nice natural progression. In fact, almost always when you list it out, it's going to be countable. All right. And f of n. All right, here's what we have to do. We have to start at 3, and we have to jump by 4s. So we're going to get a 4n, right? Since we jump by 4s, I'm taking a 4n. Now, when n is 1, I want it to be mapped to 3. When n is 2, I want it to be mapped to 7. So what we can see is if I just plug in n is 1, all right, that's going to be a 4. So I need to get rid of 1. I need to subtract 1 in order to make it start at 3, and then the next one 7, and the next one 11. Right? Hopefully you caught that, why I subtracted 1. It was so that I could match up this initial mapping. 1 maps to 3. So 1 plugged in here. So I have 4. I need to subtract 1 to get a 3. 2 goes to 7. 3 goes to 11. 3 times 4 is 12. Minus 1 is 11. So this function guarantees me that the set is countable. All right, now an interesting, very interesting problem is whether the set of all fractions is countable. All right. By the way, you've probably, if you haven't seen this before, this is the set of all rational numbers. We can think of this as actually the set of all rational numbers. Rational numbers. And in this, you can only right now see fractions like 1/2 and 1/3, so everything is a proper fraction. But I don't mean it that way. I don't mean to imply that all fractions are proper. So we could have had 3/2, and we could have had 9/7 or 9/4. That's in that set. So what I'm talking about is all rational numbers. Now, I've picked all positive rational numbers. You could do, you can imagine that if we have negative rational numbers, it's going to be the same thing. So I've picked all positive rational numbers. All right. Now, this is actually a problem that that Cantor, the guy I was talking about earlier, is very famous for. Okay, it's a very famous problem in mathematics, and is the set of rational numbers countable? And it turns out that the answer is yes. Rational numbers are countable. Now again, I've just listed out the positive rational numbers here. But it turns out if you put negatives in there, they are countable as well. So I'm not going to ask you for this proof, but I just want to show you the clever way that Cantor decided to actually prove this. All right. So what Cantor did is he said every fraction can be written as sum A over B. All right. So let's make a grid, and we're going to make a grid. We're going to have the A's over here and the B's down here. Now, when I say every number can be written as an A over B, I mean every number can be written as an A over B, where A and B are positive integers. In other words, A can be 1, 2, 3, 4, 5, and so on and so forth. And B can be 1, 2, 3, 4, 5, and so on and so forth. So we're going to get all kinds of fractions in here. All right. And Cantor said, all right, let's take 1 over 1. Let's take 2 over 1, 3 over 1, 4 over 1, 5 over 1. Let's take 1 over 2, 1 over 3, 1 over 4, 1 over 5. And you can see you get this infinite grid. Now, this grid is two-dimensional, meaning, right, there's 2 dimensions. There's a horizontal and a vertical aspect. And really the goal of trying to list out or the goal of trying to prove whether a set is countable or not is to try to make things into a list, a single list. All right, so let me finish what I was doing here with labeling all these things. We have 3 over 3. Now, don't bother with the fact that some of these are actually the same numbers. Obviously, 3 over 3 and 2 over 2 and 1 over 1 are all 1. That didn't bother Cantor. That's just a similar fraction. If we've counted it twice, all the better. And you can see if we continue this on, I can get any single fraction that I want. All right, so if you dream up of a fraction, 672 over 394, again, go 672 out on the A, go 394 down on the B, and you'll be at your fraction. Now, what Cantor saw was that if you start trying to use your map and you start going this way, then you run into a problem. So if you map 1 to 1 over 1, and 2 to 2 over 1, and 3 to 3 over 1, and you start mapping in this direction, then you'll never ever get down to the second line. And that's a big problem, because we wouldn't be a one-to-one function if we didn't get down to the second line. If we wouldn't be a one-to-one fraction onto these fractions if we didn't get down the second line. And the exact same thing happens if you take a column, right? You go down forever, and you never get back to the second column. So what Cantor did was quite clever. He said, instead of actually mapping in straight lines, either horizontally or vertically, what I'm going to do is I'm going to zigzag through this pattern. All right. So he said, let me take this 1 over 1, and that'll be my first unit. So that'll be what I map the 1 to. And then I'll map the 2 to 1/2. And then the 3 I'll map to this. And then the 4 map to 3 over 1, excuse me. And then 2 over 2 will be my fifth. And notice that if we keep zigzagging, even though it takes us a long time to get through this, we're going to eventually get to every single fraction. Okay? So no matter what fraction that we have here, eventually that line is going to get through it. Okay? And so his thing, this showed that this proves that the rational numbers are countable, at least the positive rationals. And then you can go there from the positive rationals to the negative rationals quite easily. Now, you may have the impression that all of the infinite sets are countable. However, this next question will change that. Is the set of real numbers countable? Now, the proof is beyond this course, but I will answer definitively that no, the real numbers are not countable. Like I said, I'm not going to actually prove that here or even show you that here, but hopefully you understand first off what the real numbers are. So you take the rational numbers and you throw in anything with an infinite decimal, anything like pi has an infinite decimal, square root of 2 has an infinite decimal, anything like that. There's a lot of other numbers that have infinite decimals. And it turns out if you throw in those numbers, then you'll see that, or you won't see, but you won't see here anyways, but it turns out that, in fact, if you throw in all those numbers are not countable. So we see that the set of real numbers, like I said, I'm not proving it here, but I'm just telling you, does not actually have a one-to-one function from the set of real numbers to the set of natural numbers. So it is not countable. However, it's fairly easy to see that it is infinite. So it's infinite, but not countable. So it is a bigger infinite than countably infinite. So in other words, the set of real numbers, now, by the way, the set of real numbers is often denoted, oh, I really did that poorly, is often denoted by a double bar and an R. The set of real numbers, that's, again, a poor way of doing it, but the set of real numbers is infinite, but not the same size, not same cardinality as the natural numbers, 1, 2, 3, and so on and so forth. Okay? So it's a bigger infinite, and technically the real numbers, we often say, remember these guys had aleph not as a cardinality? Well, real numbers often are said to have cardinality of aleph sub 1, aleph 1, all right? And so that's an interesting fact. Now, I will say this, we're talking about sort of layers and nests of infinity and bigger infinities and bigger infinities. And it turns out the real numbers do not have the highest cardinality, the highest infinity of them all. In fact, you can create sets that are infinite sets, which have higher cardinality than the real numbers. In other words, the real numbers cannot map onto different sets. And I'm not going to go into that, but I want you to understand that the word infinity isn't like finite. We can have bigger infinites and so on and so forth. Okay, there are many sets which have higher cardinality than the real numbers. In fact, that we saw that aleph sub 0 was countably infinite. That's sort of the lowest infinity that we can think of. The next is aleph sub 1. That's the real numbers. Well, technically, you can make sets with aleph sub 20 or aleph sub 50. Okay? So there's something called power sets that give you higher and higher and higher cardinalities. And you can have, aleph sub anything that you could possibly wish for. All right?